Welcome to Global British School. Students, this is your first year chemistry class. I'm Dr. Jadbano and we are on chapter number 2, atomic structure, and the topic for today's discussion from chapter 2 is Planck's quantum theory. Students, previously we have studied about Bohr's atomic model, and we learned there the relation of energy with frequency, wavelength and wave number. And in this topic, that is the Planck's quantum theory, after completing this, students, you will be able to define photon as a unit of radiation energy. You will call the radiation energy as a photon, and you will be able to relate energy to frequency, wavelength and wave number of photon. Previously in Bohr's atomic model, there also related the energy to the frequency, wavelength and wave number of the just radiation, but here in this case radiation of energies, they are given as the photon, and you will also be able to calculate energy, frequency, wavelength and wave number of these photons. And the important points are, you can say, the postulates, the salient features of the Planck's quantum theory are like energy is not emitted or absorbed continuously. Energy never emits continuously, never absorbed continuously, but it is in a discontinuous manner. It is emitted or absorbed, as already previously we described in the Bohr's atomic model, but here we take the energy radiation as a photon. Remember this, and this is the objective for this topic, how Planck's define the radiation energy as a photon. It is emitted or absorbed in form of wave packets or quanta. Quanta is the plural of quantum. Basically, quantum is a wave packet with the energy, and in case of light, this quantum of energy is called given the name photon. And here you can see in the first line, energy is not emitted or absorbed continuously, but it just emitted when electron jump from higher energy level to lower energy level, and it emits the energy. This energy is this wave packet is a quanta or quantum, and this quantum is given the name photon in case of light radiations. And energy is absorbed when electron move from its lower energy level to higher energy level. How much it absorbed, that is a wave packet, that is called a quantum, and in case of light, this is given the name photon. And this is a wave packet that is equal to h nu, Planck's constant and frequency. I will explain you right now. And the amount of energy associated with quantum of radiation is direct proportional to the frequency of the radiation. If the energy is higher, then its frequency will be higher. If energy is lower, then its frequency is lower. Or you can say low frequency, then lower energy, high frequency, then higher energy. And if you remove this proportionality constant, there is always a constant, that in this case this is called Planck's constant. And previously in previous lectures we have learned about the Planck's constant h. Its value, numerical value is 6.625 10 raised power -34 joule second. And this one, and basically this h nu, this is the wave packet, or you can say this is the quantum of the radiation. And here you can see that in this case energy is direct proportional to frequency. Remember this one, energy is direct proportional to the frequency. Its next postulate is a body can emit or absorb energy only in terms of integral multiple of a quantum. Let's suppose we have this quantum E equals to h nu, but it is not always a single quantum. It can be double quantum, double quanta, triple or tetra or more than this. So this wave packet or this energy, this is the multiple of integral multiple of some number, like n stand for 1, 2, 3, 4 and so on. If this is 1, then this is like one quantum. If it is more than 2, then double quantum, then they are called quanta. So basically this energy that is absorbed or emit This is in terms of integral multiple of quantum. Students, we know frequency and wavelength are inverse proportional to each other. Frequency is proportional to 1 over wavelength lambda, or you can say frequency is equal to, when this proportionality is replaced with a constant c. In this case, this is the c, velocity of light, the speed of the light, that is 3 into 10 raised power 8 meter per second. And now putting the value of frequency in equation 1. What was the equation 1? Equation 1 in E equals to h nu. So because h is constant and we have now this frequency equals to c over lambda. Putting c over lambda instead of this frequency, you can see E equals to h c over lambda. In this case, you can see there is another relation. Energy is proportional to 1 over wavelength. Wavelength and energy are inverse proportional. If a photon has low energy, then its wavelength will be high. If a photon has high energy, then its wavelength will be low. Similarly, we know nu bar and wavelength are also inverse proportional to each other. This is the nu bar. I will define in the later slides what is nu bar, what is a wave number, what is frequency nu, and what is the wavelength, that is lambda. Putting the value of 1 over lambda in this equation, you can see hc of 1 over lambda equals to nu bar. So putting this hc 1 over lambda, you will write now nu bar. So here is another relation of energy with nu bar, that is the wave number. Energy is direct proportional to nu bar. So we have three types of relations: energy direct proportional to frequency, energy inverse proportional to wavelength, energy direct proportional to wave number. And these are the conclusions of the Planck's quantum theory. How energy of photon is related to frequency. Of course, with frequency it is direct proportional, with wavelength it is inverse proportional, and wave number it is direct proportional. And now I will define you what is actually this frequency, this wavelength, and this wave number. Frequency, that is represented by nu. This is the number of waves passing through a point per second is called frequency. Hertz or cycles per second is its unit. It means this is the point and the radiations are moving from this point. So these waves, number of waves passing this through some point per second, this is called basically the frequency. If the passing wavelengths per seconds are higher, then frequency will be higher. If the passing waves per second are lower, then frequency will be lower. So this is the frequency, the number of waves passing through a point per second in a second, that is called frequency, and its units are hertz or cycles per second, means its units is per second. Wavelength, this is represented by lambda. This is the distance between two adjacent crusts or troughs is called wavelength. These waves travel in, this is the crust, this is the trough, crust, trough. So wavelength is actually the distance between two adjacent crusts or two adjacent troughs. So this distance is called the wavelength, this one. Because wavelength of radiation is already short, but this is a distance, so we measure its units in nanometer or angstrom. Angstrom is equals to 10 raised power minus 10 meter, and 1 nanometer is equals to 10 raised power minus 9 meter. So you can imagine how short they have the wavelength. So the distance between two adjacent troughs or two adjacent crusts, this is called the wavelength, and its units are nanometer or angstrom, and it's represented by lambda. The third one is that the nu bar or wave number. Wave number is symbol is nu bar. this is like frequency and 1 bar on above. This is the total number of waves per unit distance. If let's suppose you have this distance 1 meter, let's suppose, and the total number of waves in a distance, this is called the wave number. This is called wave number. Similarly, like this is again, let's suppose this is 1 meter and this is the number of waves in this, and you can see here like suppose 1 2 3 4 waves, and here 1 2 3 4 5 6 7 waves. So which one has the lower wave number? So this have this the number of waves that passing through a distance, that is called the wave number per unit distance, because this distance and in per unit distance, that's why its unit is per meter. So total number of waves like it will be 4 waves per unit per meter, and it will be just like, it's just a supposition, it's not the real. And in this case this is the 7 waves per unit distance per meter. So 7 are more wave number and 4 is the less wave number. Now this example will explain you how energy can be used to convert this photons energy into frequency, wavelength and wave number. First one, photon of light with energy. So you have given only the energy, 10 raised per minus 19 joule is emitted by source of light. Convert this light into wavelength, frequency and wave number in terms of, so wavelength you have to calculate in meter and frequency in hertz, or you can say per second, and the wave number in per meter. And the second part, convert this energy of photon into ERG. So now you have to change this energy from joules to ERG and then calculate wavelength. Now you have to calculate wavelength in centimeter and frequency again in per second, and the wave number in per centimeter. First I will solve you here for part 1, and I will explain you part 2, but you have to solve the part 2 for yourself. This will be a practice question. Part 1, first of all write the data. Energy of photon is given, you have to calculate wavelength, frequency and wave number. So recall the equation about the energy and frequency, that E equals to h nu. That very simple. H is Planck's constant, 6.62 10 raised per minus 34 joule second. Frequency you have to calculate, energy value is given. This is very simple, just you have to put the values and solve it. This is the energy, Planck's constant, frequency you have to calculate. Then keep this here and divide the Planck's constant by energy, you find the frequency. This is 1.51 10 raised per minus 14 per second. Now use this frequency and recall the relation between frequency and wavelength. That was, frequency is equal to C over lambda. Frequency is equal to C over lambda. Lambda is C over frequency. Frequency you just calculated, and C, you know, this is the velocity of light, speed of light, that is 3 into 10 raised per 8 meter per second. Just put the values and you can calculate the wavelength of the radiations of the photon. And now recall the relation between wave number and the wavelength, that nu bar equals to 1 over lambda. You have lambda, you have value of lambda here in this case, divide 1 over lambda this, and you can find the wave number, nu bar of the radiation. So in this way you have converted the energy into frequency, wavelength and wave number. Now the part 2 is that convert this energy into from joule to ERG. First you know what is the relation between joule and ERG. 1 joule is a bigger unit, ERG is a smaller unit, and 1 joule is equals to 10 raised per 7 ERG. So first convert the energy given into ERG. That was 10 raised per minus 19, so multiply with 10 raised per 7, adjust minus 19 and 7, this is equals to 10 raised per minus 12 ERG. So this is your energy, and because you are using Planck's constant, and that also has a unit of joule second, so now you have to equate the units everywhere. So you have to convert the Planck's constant value in ERG. Previously it was 6.625 10 raised power minus 34 joule second. Now multiply that with 10 raised power 7. So minus 34 plus 7, they will give you 10 raised power minus 27 ERG per second. ERG second. And the velocity of light, because in this case they have asked the wave number in per centimeter, so you have to convert the speed of light into centimeter too. Meter is a larger unit, centimeter is smaller, so you have to multiply meter with 100, that will convert into centimeter. 3 into 10 plus 8 multiplied by 100, it will give you 3 into 10 raised power 10 centimeter per second. Now you have all the values. You have the energy, this one, you have energy, you have Planck's constant, you have C. Just you have to recall the three equations. E equals to h nu. Put the values of energy and Planck's constant. You will find the frequency. With the help of frequency, find the wavelength, that is equal to C over V nu bar. And with the help of equation nu bar equals to 1 over lambda, you can find the nu bar. So this is for your practice. Calculate this on your notebooks, and you will be able to understand how energy is related to frequency, wavelength and wave number. In this way we obtained our learning outcomes. So this was all about the Planck's quantum theory, that was about light radiation. And our next topic will be X-rays. In X-rays you will learn its production, its properties, relation of X-rays with the atomic number, and also its uses, or you can say its applications.